And first, thanks for everyone for staying. I'm almost the last session in the show, so and I see some familiar faces. So great. I'm going to speak to you about how to try and utilize GPU as a service on Kubernetes. I'm Yaron. I'm CTO for Iguazio. And first, before we start, some motivation is when people build today machine learning pipelines or machine learning-based applications. When I say application, I mean they don't use machine learning just for reporting and doing something along that line. They're trying to actually embed machine learning into their application. We see that building the machine learning models or the algorithms is really easy, but doing everything else is complicated. So you see that some projects that start with few weeks of POC end up with 6 to 12 months of deployment. And some of the reasons that those things take time is that the first step of development is relatively easy. You write some code, and then some people make it a container. Data scientists are usually not too educated on that space. You need build and make and all that. And then you're starting to hit scale. So you need to think about how do I scale out? And scale out requires distributed computing. And distributed computing comes in many forms, load balancing, sharding, partitioning, hyperparameter, et cetera. And then comes an aspect of tuning. Tuning means how do we turn things to more asynchronous, more parallel? How do we embed GPU support into those same code? How do we cache elements that we don't go over and over to a database? How do we tune our queries to be more efficient, and et cetera? And then we need to think about instrumentation. Instrumentation means like starting to do logging and monitoring and maybe versioning of our code and Git and all that stuff. And then eventually, once we got everything working, we wanted to make it repetitive. So we need to add automation. So CI/CD, workflows, pipelines, rolling upgrades, because things are running in production, A/B testing. So you see there's so much work to do where usually the first part is few weeks. The second part is a lot of months of many, many people. One of the things that we're trying to do we're promoting a bunch of open source projects, including this one, Nucleo and others, is essentially automate all this work of all those pipelines. And part of it is automate the integration of GPUs and dynamic allocation of GPUs. So everyone here that thinks of GPUs probably thinks of deep learning, TensorFlow and all that. So there is some news. GPUs are used to do many different things, not just deep learning. Anyone familiar with the NVIDIA Rapids, for example? OK, good. So this is part of a joint blog we did together with I did together with NVIDIA that just demonstrate analytics use case, taking some JSON, very large JSON data. Very typical use case, you have weblogs, generate a lot of JSON-related data. You need to build aggregates on top of that data, and then dump the aggregates or the processed data into sort of some files, Parquet. That's something that you would usually do in something like Spark, but that will require a lot of work. Just writing some Java class takes more work than doing everything here combined. So one of the things that you can see in this very simple code is that running this with cuDF, which is the data frame, pandas data frame with GPU acceleration, takes about 1.4 seconds, and running the same thing on traditional pandas is 43 seconds. So 30 times faster, exactly the same code, just changing the import on your Python. So obviously, there is a very big advantage of using GPUs. There is one challenge, though. GPUs are usually more expensive, although NVIDIA T4 and some other technologies are now lowering the barrier. And we don't want to pay for their idle time. So until now, every time you hear GPU as a service, the common thread I'm seeing is usually GPU partitioning or fixed allocation of GPU to different tasks. So you're saying, OK, there is a container. I'm going to attach a GPU to that container. Let's assume it's a Jupyter container. I'm not doing any work. I still pay for that GPU. So what we want to do is essentially attach the GPU only when we really need them for processing workload. OK. So how would we design such an architecture of a complete data science platform on Kubernetes? This is also something we do for a living, but because it's an open source ecosystem, everyone can build the same. We need the first layer of data. Data comprised of online and offline features usually. So things that are more like object store, data warehouse, Hadoop, file system, and then things that are more real-time, like time series, key value, caches, etc. This Rapids thing also know how to accelerate databases. We use it in our product, but also there's Blazing SQL. There are other SQL-oriented projects that know how to leverage the GPU acceleration and run queries really, really fast. The next level, we need resources. Resources could be GPUs or CPUs. Even CPUs have quite a bit of optimization that you could use. There's, for example, projects from Intel that know how to use the AVX instruction set to run TensorFlow faster. Okay? So we need to think about those things. We have Kubernetes, and then we have a set of services that deal with machine learning, data science, et cetera. And then we have a layer where people actually use all those things. Usually, if you look into a KubeFlow environment, you have managed notebooks, you have pipelines, we promote the notion of serverless, and you need other things like job management, artifact management, and I'll try to demonstrate all of those things in a minute. So how would we build a pipeline? The pipeline usually comprises of different steps. The first step is ingestion. Ingestion means we need to go and bring data in order to process it, usually denormalize it in a machine learning use case. Then we run a training on that. Once we have training, we need to generate models, and we do model serving. Many people forget that model serving is not the last mile, because model serving usually gets some sort of a NumPy array, and the real data is not NumPy arrays. Real data may be pictures, maybe customer IDs. So we need another component, which is this sort of API, gateway, or sort of an application to translate real data into models. And we'll show that in a minute in a demo, how we build all those things. Now, all of those steps can use GPUs. Okay? Today, with things like Rapids and other libraries coming, you can essentially use GPU acceleration across all of those different steps. Now, one of the things that we want to do in order to make it simple, this is, by the way, a real end-to-end application for real-time product recommendation that we've implemented in several places. It's about collecting data which is offline, like ETL, records about users, getting data like real-time transaction and cart changes, real-time location information of users, scraping data dynamically from things like weather services, then again, denormalizing the data. And what you could see is that in many use cases, you actually combine machine learning and deep learning. It's not just deep learning or machine learning. Things like embedding and product-to-product relations are very well implemented on deep learning, and things that are more regression-oriented may actually run better on machine learning. And even those things are have dependencies. You have to finish the first step of training to do the second step of training. So this is essentially a pipeline, and what we're trying to promote is a notion of functions. Instead of thinking of everything as containers and allocating them, or notebooks, or VMs that have resources attached, think of everything as elastic function, as things that can grow, shrink, and even shrink to zero. If they shrink to zero, they don't consume any resources, okay, which is a great thing. And those things are just interleaving of data sets and those elastic functions. One of the important things, by the way, is when you're doing serving is how do you get data in sort of more real-time concurrency, but that's on a separate topic. So what we've designed is a notion of functions, again, very elastic, can scale all the way down to zero. And those functions have very abstract code within them. They could have Python code, like this function that's doing the same thing of real-time analysis of JSON and aggregation and dumping of this JSON. If you're going to run exactly the same function inside a container, because of all the concurrency issues of Python and lack of parallelism, this will only going to get you about 20 megabytes per second. If you're going to run exactly the same function without modifying anything within a real-time runtime that can also attach to GPU like Nucleo, it will get you about 600 megabytes per second. And T4, if you look at, that was tested on T4. T4 is not that expensive. The GPUs sort of relatively low cost. So maybe twice as more expensive, 30 times more performance on this architecture. But the other key advantage of serverless is not just usually it's not associated with performance unless you're using Nucleo, but the key advantage of serverless is the elasticity and zero DevOps. So I can write this code, click deploy, and it just works. It auto-scales. It has logging, monitoring, instrumentation, full integration with KubeFlow pipelines, and all that out of the box. So again, simplicity, ease of use, time to market, along with extreme performance. Another use case is the serving part. So we want to use functions for also serving models. Again, one of the tricks that engines like Nucleo now know how to do is maximal utilization of GPUs. How do they do that? Small trick. I can tell you the secret. It's essentially creating sort of an elevator against the GPU, have multiple workers. It always fills the pipe of work towards the GPU. So then the GPU is always 100% utilized. And what you're getting in this example is 4 times more transactions on exactly the same code that you've written. Okay? Or if you use half of the machines, you're still twice as fast. So using something that's more optimized to work with GPUs can be 4 times more cost effective. Now, beyond just having the performance, again, the simplicity is the important part, is how do I elastically scale, and how do I work within my notebook and convert my notebook to this real-time function that runs 4 times faster and dynamically allocates GPUs for me. So this is another part. But the biggest challenge is not the ingestion and the training or the serving. The biggest challenges are the data preparation and job and training. And for that, we've developed a new concept, which is ML functions that are more batch-oriented. They leverage distributed computing. And those things that when you launch a job, they will dynamically allocate resources. By the way, everything I'm speaking about is open source project, and I'll give you the references in a minute. So everything that you launch will get dynamically attached to GPUs. That means that if I'm running, one approach, again, to GPU sharing is, I'll have a GPU. There are some companies that know how to partition the GPU to 2 virtual GPUs. You get half, you get half. So it reminds me of the Solomon, in the Bible. And the point is, instead of giving you a half and you a half, maybe I can give each one of you a burst of GPUs for the sake of running. You'll run 10 times faster, and that will be way more efficient. Also, when I give you a half and you a half, what happens with all the residual data? You're running a job, you use some memory in the GPU. There's no real way today to isolate memory in GPUs and resources. It's not like CPUs that you can say, you are going to get this amount of memory and you're going to get this amount of memory. So you rather use it more like in HPC paradigms where you just burst, everyone gets everything, finishes as quick as possible, and make room for the next guy. So essentially what we've built is thinking of serverless in mind. What is serverless? Serverless is elastic scaling. It's essentially pay-per-use. You only use resources when you need them, and no DevOps. So in order to build something like that, we now need to adopt it to different types of distributed engines, like Spark, Dask with Rapids, etc. So what we've done is we've taken the approach of serverless and decoupled the engine that does the distributed data processing from the automation of container build and controllers and event loop and run and artifact management and all that. And I'll show it in a minute. And also what you want to do is reusability. So you want to be able to create templates and reuse them in different places, move them into pipelines, debug them, create different variations over time. So this is one of the projects that we've initiated. And the way that it works under the hood in order to get this effect is think about building a sandbox that can run on many different environments, whether it's Spark, Dask, MPI Job, Harvard, any type of operator, even managed services. And this thing, when you run a job, you essentially need to pass 3 things. Parameters. You need some credentials, because your job may access some database. And you need data. And when your job finishes, it generates some artifacts. Artifacts are results, operational information like logs, telemetry data, et cetera, and data. models, data sets, etc. So you essentially create a sandbox where you run your code within a runtime. The runtime is this thing that's in charge of how you create parallelism. And parallelism in data science is very different for every task. In some cases, you'll use hyperparameter. If you're doing Spark, you'll use RDDs. If you're doing Dask, it has distributed data frame construct, etc. In Nucleo, there's multi-threading, lightweight threading. So every framework will do its own. So you essentially tell the framework, you go do your parallelism, and it will do it the best way it can. So there are about 8 different engines currently supported under this framework called MLRun. And they know how to allocate resources dynamically. So I can pass parameters, inputs, secrets, etc., get it to run extremely fast, and then collect the results. And there's another interesting side effect. It's glueless integration with KubeFlow pipeline. And I'll show you how it works. Okay. So with all that, let's look into some demos. So I'll show you 1 or 2 demonstrations. The first one is sort of deep learning, which is essentially very optimal for GPUs. And what we want to see every time we have a pipeline, it essentially comprises to about 4 steps. One is the data collection. Then we need to do some massage to the data, in this case labeling, because it's image processing. The next thing we want to do, we want to run our training on a distributed set of processors. And then we want to create deployments and test against our deployment. Okay. By the way, everything I'm showing is in this repo called mrun/demos. Any questions, or okay, we'll leave them to the end. So let's look at this use case. We said we have 4 steps. First step is data collection, then labeling, and then training. So what I want to define is functions. Okay, hope it's clear. I want to define functions. So essentially, when you're doing sort of more training and batch, you don't want to do event-driven functions. You want to pass parameters to functions. So think that you can run a function. This is a function that opens an archive, like a zip, in S3. In this case, it has a context as an option and a bunch of parameters, like where do you want to dump the data to, where is it coming from. And this function has a context object, which is pretty cool. So with the context object, if any of you know MLflow, heard of it? So 1, okay, 2, 3. Okay, we'll get 10 at the end. But there's a notion of logging. When you run any experiment, you want to be able to log the outputs of the model, so then you can version them, and you can repeat automatically those experiments. So the context allows me to do things like logging, labeling, tagging, time series for monitoring, telemetry, logging artifact, etc. So I can log my results of the first step. Then I have a labeler function. Again, get some context. Where all the pictures are. Where do I want to dump the results of the labeling, which is essentially 2 things. One is a category map, and the other one is a data frame with labels for every image. Again, those things are logging the artifacts. And then I want to execute those things. So the first thing you want to do is debug the functions. You don't want to run it on a pipeline in the cluster, because if you have a small bug, you forgot a point somewhere, whatever, you don't want to go to the cluster. So you can just go and create what we call a function. If you don't specify what we call a runtime, it essentially means here, in the notebook, in PyCharm, wherever you're running. So you can essentially define a task. The task is those inputs and outputs. Run it locally, and it will just run in your notebook and record everything that we just said, artifacts, etc. The next thing I want to do, I want to take the results of that sort of import function and do labeling. So again, I can just go and create another function from the local notebook and essentially execute, and I'm done. And the third thing I want to do is training. The problem with training, it really requires a lot of resources, and that's something I don't want to run on my notebook. I actually want to run on my Kubernetes cluster. So I don't need to build YAMLs. I don't need to do Docker files, all those crazy things. I just want to run my function. So I can take my function, which is just doing training with TensorFlow and Keras, I want to pass some data, some parameters, sorry, into this function, the image sizes, the source directories, number of epochs, et cetera. And I want to also provide some data sets into that function. And I want to create a function. This time, this function, I'm going to tell it that it's running on an MPI Job operator, essentially distributed TensorFlow. So instead of running locally, I'm just telling this function, look, you're essentially running on Kubernetes on an MPI Job operator. And maybe I want to attach some other things like, give it a volume mount and give it a number of replicas and maybe giving it GPU. And now I want to run it. So now when I'm doing run and it looks like it's running on my notebook, it's actually not running on my notebook. What this engine does is essentially packing all my code, my dependencies. If it needs to build, it will build, generate the resources on the cluster, and running it, having a control loop to make sure this thing is really running and not crashing, and gathering all that console, a lot of other things, and all the console is essentially being grabbed directly into my notebook. So I get the cozy feeling that it's running on my notebook. Essentially, it's running on a very powerful cluster with GPUs and multiple nodes, okay? Now, the point is that once this job is starting, is essentially only then it's allocating GPUs. So that means if you have a bunch of data scientists and you have a pool of 10 GPUs, each one can just grab a bunch of GPUs, run his job. After five minutes, it will finish, and he goes do another thing. Instead of partitioning your GPUs to multiple people and paying more money for more GPUs. So all this thing can run, and eventually you may have some results out of that run. And the last thing we want to do is deploy the results. So again, here we need another function, but this time it's not a batch function, it's a real-time function. It's what we call nucleus serving function, which is, anyone knows what's KF serving? Good. So one challenge with KF serving is that you still need to build, make YAMLs, Docker, all that stuff. Nucleo is a real-time engine, service engine, so we now let Nucleo essentially run off KF serving models, and it could even be extended like this example. KF serving models only accept NumPy arrays as inputs because Nucleo is very flexible. It could even accept JPEG images, and I show it in a minute. So essentially what I want to do is just create a function. I can even create a function from a notebook or from a class. And the only thing I need to say is deploy. That essentially automatically creates my model into production. Part of the function specification, I can even specify like number of workers, threads, number of GPUs, et cetera. And I'll show that in the UI in a minute. So essentially, I can dynamically create those functions. Those functions would elastically scale to meet the load. If I need more transactions per second, essentially, it will use more GPUs and more CPUs. If I don't use any, this function essentially scales to 0, doesn't consume any GPUs and any resources. And once I have this function up and running, I can just throw some pictures at it, some cats, okay, some dogs, and it will respond with the right classification, hopefully. Yeah. So, but another interesting thing that you can see that the content type here is JPEG. And the content type here is text. So in this case, I generated the URL of the picture. And in the second case, I actually sent binary image. If you are using something like Seldon or KF serving, that means that you need to have another function that translates your image into a binary list, into sort of a byte array or sort of NumPy array, and only then do serving. 2x amount of work. And another interesting thing on Nucleo doesn't only support HTTP triggers, it supports Kafka, Kinesis, about 14 different triggers, including all the complexity and scaling associated with them. So if you use Kafka, what you need is auto-scaling, or in checkpointing and restarting. If you have more load, you want to essentially serve those shards of more processes. So Nucleo automatically knows how to scale itself if there's more load. And when you're doing streaming, you have to deal with orders and all those things. It knows how to checkpoint, split, rebalance, and go back to the same pointer. So again, all of that is masked from you. You don't need to think about any of that. Now the point is, after I've done all of that, the next thing I really want is to automate, because we don't want to build those things over and over. So what I can just do is something very simple. I can create a KubeFlow pipeline, but just daisy chaining functions. Any of you played with KubeFlow? Someone succeeded to generate an artifact by himself? Only one. Now, I know it's a pretty big problem, but I'll show you how you don't even need to do that with this framework. So what we need to do, what we want to do is not like the KubeFlow thing of, container ops, YAMLs, all that stuff. What we want to say is we have functions. We want to daisy chain those functions. So essentially, I have a function. I want to view that function as a KubeFlow step. I want this function to have inputs, outputs, and parameters. And maybe I want a daisy chain. So my training function essentially needs to take the labeling function output called category map, et cetera. And my deployment function actually wants to take the training model result and deploy that. So the only thing I need to do is I can create this workflow. But I can even put this workflow in a function that listens on an HTTP event. If you want to re-trigger your KubeFlow, recreate your KubeFlow pipeline every time there's a GitHub update, you can even do that by turning this workflow into a function itself. Okay, and once I have it, I just launch KubeFlow client, and it will actually run. And there's another interesting thing here. I can even watch the result in real time. So with that, I generate a KubeFlow pipeline. And if you want to know what is the result, I would just go to KubeFlow. And I could see all the results of my training with the artifact. One of the reason I highlight this, anyone that really tried to generate artifact in KubeFlow, the way it works, you have to generate JSON files in specific folders with a lot of boilerplating. Here, I didn't do anything to generate that. The minute I said log artifact, it automatically knows how to program KubeFlow in order to make sure this thing is actually being visualized. And all the inputs and outputs of my job are being visualized, all my logs. This is the training. This is the deployment step. You could see the deployment step automatically turn my function into something that actually runs on a specific endpoint that you see here. So again, everything is automated, very little amount of work. And also, MLRun has a UI. It's now being reworked with some UX people. But essentially, everything that runs, everything I did in the notebook, as a job, as a pipeline, not just limited to pipeline, could be tracked in real time. So essentially, when I'm doing my training, I can see where is it running, all the labels, even labels that you can add within your job. I can see all the inputs to the job. I can see all the things that were generated by the job and even download those. The same thing. I can see the logs of my job. Okay, and those will get updated frequently. I can even see all the artifacts, sort of see everything from a versioning of data and artifact view, very similar to MLflow, just more comprehensive and suitable for Kubernetes. And it's not limited to deep learning. There are many different use cases here in the demos. There are also machine learning. One of the interesting machine learning examples is also using a built-in hyperparameter tuning, because we said that the engine themselves know how to deal with parallelism. So let's assume I want to run the same XGBoost example with multiple parameters. I can just pass the grid or the different combination, and it will essentially distribute it or all those different experiments into all those engines, containers, and threads in parallel. So one thing that KubeFlow doesn't know how to do today, and is sort of being addressed by this framework, is that each one of the steps in KubeFlow today is a single container. What happens if you want to apply parallelism? Like in this training job where we actually use 4 containers, it's very hard, almost impossible to do in KubeFlow. So with what we call MLRun, then you can essentially, every step could actually be many different things that run in parallel with full parallelism and high concurrency. And each one of those can attach to GPUs dynamically. And if you want to look at the actual function, you can even look into them through a real-time dashboard. You could see how much resources they consume. You could see their logs. You could see what's the current amount of containers that they're using. You could scale to 0. You can even look at the code. You could change the resources. Everything that you see here was auto-generated. It actually tells you that. I think here, this code was auto-generated from my from my Jupyter, sorry. But you could see that it essentially can configure all the resources, all the environment variables, volume mounts, all that stuff. It's not stateless. You can actually attach storage and volumes into Nucleo functions. All my package dependencies was sorted up automatically and generated. And And I can even change the triggers. Right now, it's using an HTTP trigger. If I need Kafka trigger, it's as easy as saying, give me Kafka. These are the endpoints. And all the auto-scaling, checkpointing, all that is sorted up for you. Another interesting thing, and because of this GPU sharing notion, then I have this sort of elevator effect that I have a bunch of workers hitting the same GPU, so the utilization of the GPU is much higher when it's running within a Nucleo engine. Okay, and there are a bunch of blogs on that from NVIDIA and from my company. So that's on that front. I think that's sort of it. And any questions or things that you want to learn? How long do we have?
How do you prevent someone from consuming all of the GPU?
So that's something that is still not in ML Run, but we're working on it, because think of it, there is a controller. And when you submit the jobs, it hits a controller, and the controller generates essentially the Kubernetes resources. It's not in the current controller, but we're working on essentially adding sort of admission control in the controller itself. But that's something everyone asks for. Another interesting thing, if you're in the cloud, what the controller will do will actually increase your Kubernetes size if needed. Okay.
Is there a performance difference between using the GPUs in Kubernetes versus just bare metal machines with GPUs?
Same performance. Because if you think about what GPUs are, what Kubernetes is or Docker is essentially just a process. The hit in performance is usually when you think about like networking and storage and things like that go through another layer of abstraction. In our solution, there is a notion of a real-time fabric, even memory-based real-time fabric, so you even don't move data across steps. You essentially just move pointers, so there's no even penalty on data movement. But usually, if it's just about computation, there's no penalty on moving to Docker. Okay.
Hey, if I have an existing TensorFlow code, how would I go about using it, I guess, wrapping it in this framework?
So you can use your existing TensorFlow code, and essentially what the runtimes do, you can have a job runtime, which is essentially just your TensorFlow code. But if you want to use the MPI job, again, it's again sort of a TensorFlow Keras model, but there is one line that you need to add somewhere. Don't even remember where, which is using Horvath. Sort of, it's nothing to do with this framework. It's how you would develop for a distributed TensorFlow. You need Horvath, and then what you see here at the end of the code, the logging is done with the rank 0. So the master, only the master is essentially doing the logging of all the results of the experiment. But that's like anyone that works with Horvath or MPI Job know how to do. Yep. Yep.
This is pretty impressive. There are a bunch of features that KubeFlow doesn't have today. Are you working with them at all to steer that into pull requests? Or
yeah, so we're contributing. Actually, one of the main things I'm doing is removing all the GCP-specific things there and moving them to environment variables. But yes, we are doing a lot of work in the community as well.
Cool. I think we have enough time for one more question, if anyone has one. Or not. Cool. Thank you.
Welcome.